It's got its own like charging and sensors. So it's designed to take magnets, but they're like 3-volt magnets. It's naturally going
Hi, I'm Peter John Walter, and this is Kevin Duxbury. We're the team behind the Feedback Lab.
Virtual reality is becoming much more widespread in today's society. Along with hand detection systems such as the Leap Motion, there has been a lack of feedback systems to complete the immersive experience. We've designed our Feedback Glove for this purpose, to make virtual reality more engaging and human interaction with the virtual environment more natural. We've taken a novel approach to haptic feedback that relies on magnetic interactions. The feedback is provided by a permanent magnet situated inside a solenoid. A 12-volt peak-to-peak square wave is sent through the solenoid, and this causes the permanent magnet to vibrate back and forth at the same frequency as the square wave. This vibration is the feedback to the user. The actuator is attached to the fingertip of the glove, and the solenoids are connected to the driver circuitry and respond to control signals from the microcontroller.
The control system for the glove sits on the back of the hand and consists of two sections, the microcontroller and the control circuit. These two work in conjunction to produce the signals needed to drive the actuators. The microcontroller is instructed through UDP packets it receives over a local network. These packets determine the behavior of the glove, either to change the current frequency of the output or to turn the output to a particular finger on or off. For every finger that's switched on, the chip sends the drive signal to run the actuators.
One obstacle was that the chip's logic level is not strong enough to produce a good response from the actuator. To resolve this, the drive circuit is used to increase the strength of the signal.
To test whether our system improves the experience, we designed a simple task for a user to complete, consisting of simple interactions with a menu. The user must make an object match a randomly generated one by navigating 3 menus for shape, color, and pattern. We timed users completing this task with and without feedback to compare how effective the glove was in improving the user experience. Through testing, we found people performed up to 33% better with the feedback, and 8 out of 10 people thought the feedback helped them perform the task.
The motivation for this project arose when using the Leap Motion in conjunction with the HTC Vive. It was noticed that a sense of touch would dramatically improve the immersion. Research into the area showed that there had been no attempt to create a device to achieve this goal that relied on the interaction between a pair of magnets. As such, we decided to develop a design to test if this approach was viable. The actuator is the device that actually provides the feedback by converting electrical energy into magnetic and kinetic energy. It consists of the solenoid, the permanent magnets, and a plastic housing. The design of the housing plays an important role in how the feedback is actually felt. When the coil is pulsed, the permanent magnets and the coil briefly have magnetic fields that are not aligned. The permanent magnets try to change orientation so as to align these two magnetic fields. The easiest way for this to occur is if the magnets actually rotate, but if the actuator housing prevents them from doing this, they will actually be pushed apart. As such, the actuator housing is designed to have a tube in which the magnets are situated so that the solenoid pushes the magnets along the tube when energized. The length of this tube dictates how long the magnets can accelerate for, and this determines the force with which they collide with the user's fingertip, and hence affects the strength of the feedback. The coil sits around this central tube so that the magnets are located in the position of strongest magnetic field, as generated by the solenoid. This makes the interaction between the two magnets as strong as possible and results in the largest impulse on the magnets. This impulse is what is actually felt as the feedback. When the actuator is attached to the glove, a membrane is sewn over the top of the tube that contains the magnets to prevent them from escaping the housing, but still allows them to press up into the pad of the finger. Our tests showed that the coil should be energized with about 6 volts in pulses to provide a strong feedback response. However, the microcontroller only has 3.3 volt logic, so additional circuitry is required to provide more energy to the coil while still being able to control the state of the actuator. The circuit for driving the actuators required a few iterations to get right. The initial design was a fairly straightforward circuit consisting of an NFET transistor in series with the solenoid. The input signals were sent to the gate of the transistor and thus controlled the state of the actuator by either allowing current to pass through the series connection or blocking it. Thus, when the transistor is turned on, the coil is energized, which creates the feedback. When the transistor is turned off, the actuator remains inactive. The input can be pulsed to create pulses of feedback, which were found to provide a better stimulus than constant pressure. The limitation of this design was that it only worked if the actuator was positioned in a certain orientation that allowed gravity to return the system to its initial state, where the permanent magnets sit inside the coil. This is important given that the actuator is to be placed on the fingertip, and as such, the user would have to keep their fingers in that correct orientation, which is obviously impractical. Instead of relying on gravity to return the system to a workable position, the circuit can be redesigned to drive the solenoid in the opposite direction and pull the permanent magnets into the actuator. This, however, presents a problem of how to actually achieve the 3 different states required. That is, pushing the magnets out, pulling them back in, and turning the actuator off. The solution was to use 2 inputs to the circuit. So in the case where both the inputs are logic 0, both of the NFETs are turned off, and this prevents any current flow through the circuit and therefore through the coil, and this deactivates the feedback. In the case where one of the inputs is logic 1 and the other is logic 0, one of the NFETs will be active, and the diagonally opposite PFET will also be active. This allows current to flow through the circuit and through the coil, energizing the coil. As we alternate which pair of transistors is active, we alternate the direction of the current through the coil. The final case is when both inputs are logic 1. In this case, all 4 transistors will be active, and current will flow straight through the transistors and short out the coil. This will possibly damage the transistors and is a highly undesirable state to be in. To make the device portable, the circuitry needs to be attached to the glove. However, we require 5 of these actuator circuits, so to achieve the required space economy, we need to use a printed circuit board or PCB.
There are a number of important factors we considered when selecting a chip to use. Most importantly, it needed to be small enough to fit on the back of the glove, but still include 10 outputs, 1 pair for each finger's actuator, as well as some form of wireless communication. The chip we chose was the Adafruit Feather MO Wi-Fi. It ticked the box for size and number of outputs, but had a few advantages that made it the best option for us. The built-in Wi-Fi module with antenna, as well as the chip's compatibility with the Arduino IDE, made it very easy to set up to communicate over Wi-Fi. Being compatible with the Arduino IDE meant that there was easy access to code to deal with the received UDP packets. The Wi-Fi module could function on a low power mode that would use around 10 to 12 milliamps, compared to the 70 milliamps of other Wi-Fi chips such as the ESP8266. This kept a fully wireless design possible, as it would increase how long a battery might last. Although this isn't something we were able to include in our design, it is where we envisioned the design going, so this was still a useful feature. The main problem with our chip was that although all the outputs were PWM enabled, we could not easily change the frequency of the PWM outputs, with it being nearly impossible to reduce the default frequency to the required range of about 1 to 100 Hz. Although we solved this problem in software, having this feature built into the chip would have greatly benefited the design, increasing its flexibility and usability. One of the serious hardware limitations we had to deal with was that our microcontroller couldn't easily change the frequency of the output signals it produced. This meant we had to control the output in software ourselves. We did this by simply repeatedly writing a digital high followed by digital low to the output in question. Each of these would be separated by a delay which was calculated so the resulting frequency was as desired. Since the frequency we used for the glove was fairly low relative to the frequency of the chip's clock cycle, the time it takes to process the commands for the digital writes and other associated code are negligible, and their delay doesn't impact on the resultant frequency of the output. In addition to the process of the digital writes, the microcontroller must periodically check for new packets that have been received. Because of the nature of sequential programming, we implemented a polling loop to check for and deal with packets as they're received. We mainly stuck to 50 Hz for our signals since low frequencies have a longer delay, which can detrimentally affect the delay before the next check for packets. Communication occurs using UDP packets over a local network. This was chosen because of the need for a low latency connection between the host computer and the glove. Also, UDP automatically ignores any lost packets, which is preferable since we're dealing with a stream of data. There are 2 kinds of messages that are used, those that turn a finger's output on or off, and those that change the current frequency of the glove. Each message starts with a keyword to denote what type of message it is, followed by the command arguments like the frequency value or the identifier for the finger being changed.
We used the leap motion sensor for hand tracking, and this was primarily chosen due to the ease of implementing hand tracking into a virtual environment with this sensor. In particular, the leap motion was designed to be used in the Unity game engine, as it's very well supported and it's easy to import leap motion data packets into Unity. This made it very easy to set up programs in Unity to test the usability of the feedback glove in a virtual environment. Additionally, this sensor was capable of actually tracking a hand when wearing a glove. In practice, however, we found that the leap motion system had a number of limitations. Firstly, although the leap motion could quite reliably track hands, it would only do this within a very specific field of view. If the user moves their hands outside of this region, the virtual hand would disappear from the user interface, and user performance could be severely impeded by trying to re-establish tracking. This was also compounded by the fact that large movements by the user often translated into relatively small movements in the virtual environment. These resulted in quite a small region of the environment in front of the user that could be interacted with by the user. Perhaps the largest limitation for our purposes was that it wasn't always reliable in discriminating between the fingers. This made it challenging for the user to interact with the virtual environment. In light of this, we think it would be quite useful to develop a more reliable system for tracking hands. Perhaps this system could include other sensors to cover the blind spots the leap motion has, or even building in beacons into the glove to provide more information on the state of the fingers.
The test application we used consisted of a simple task that was completed by navigating menus in the virtual environment. The user would be presented with two randomly generated objects, each varied by its shape, color, and pattern, the generation ensuring that none of these were in common at the start of the task. The user would then navigate each menu one by one to get the objects to match. The program would time how long it took from the first menu being pressed until objects matched as a measure of how well the task was performed, with the objective to compare how well the task was performed with and without the feedback from the glove. The user would perform the task with feedback and without feedback 3 times each, alternating which was done first for each participant so as to mitigate improvements simply due to the user gaining more experience with the task itself. The result of testing this across 10 participants was an improvement of between 10 and 33% when the feedback was turned on. This supports our idea that including feedback for interactions in virtual reality, particularly in using the user's own hands, improves their experience and makes it easier for them to complete simple tasks such as interacting with a menu. This suggests that this is a valuable area to investigate further to improve people's experiences with virtual reality. In particular, we identified a number of areas that could help refine this kind of system even more. This shows that leaving out a feedback system for hand interactions in virtual reality limits its potential, and their inclusion will help complete the immersive experience of the user. It was found that haptic feedback not only enhanced the experience for the user, but also improved the accuracy and efficiency with which they were able to interact with the virtual environment.
Some possible future improvements for this project may include a fully wireless design, improved tracking system focusing on the sensitivity, accuracy, and range of the sensor, a hand-washable device, and improving the consistency of haptic feedback strength across all the actuators. We'd just like to say thank you to Jonathan Lee, our supervisor of this project, and thank you very much for watching.